All right, we are about to journey into some of the most extreme, most mysterious objects in the entire universe. I mean, these are places where our understanding of reality just completely breaks down, where gravity becomes this absolute tyrant, and nothing, not even light itself, can get out. We are talking, of course, about black holes. You know, there's a certain poetry to how we try to describe these cosmic monsters, and this phrase really sticks with me. A hungry maw of other worlds. It just perfectly captures that feeling of an abyss, right? Like a one-way door in the very fabric of the universe. So what exactly are we dealing with here? Let's start with the central question that kicked this whole thing off. Just try to imagine this. What if a gravitational pull could get so immense, so ridiculously strong, that not even the fastest thing we know of, light, could escape its clutch? What would that even look like? Well, the thing is, it would look like nothing at all. Just absence. Now, you might think this is all a 20th century idea, something that came straight from the mind of Einstein. But the truth is, the concept is way older than that. To find the very first prediction, we've actually got to travel all the way back to the 18th century. Okay, so to get how they figured this out, we need to talk about one key idea: escape velocity. Think of it as the getaway speed. If you want to launch a rocket from Earth and have it never fall back down, it has to be going at least 11 kilometers per second. Everything with mass has an escape velocity, and the more massive and compact an object is, the faster you have to go to escape it. And this is where the sheer genius of guys like Jean-Michel and Pierre-Simon Laplace comes into play. They were just using Newton's laws of gravity, and they thought, okay, what if a star were so massive and so incredibly dense that its escape velocity was actually greater than the speed of light? Well, if that happened, then particles of light would get pulled back by gravity, kind of like a ball you throw up in the air. The star would be totally dark, invisible. It's an absolutely brilliant prediction made hundreds of years before its time. But as brilliant as that early idea was, it wasn't the whole picture. To really, truly understand these things, we needed a completely new way of thinking about gravity itself. We needed a revolution. And that revolution, well, it came from Albert Einstein. So I want you to forget everything you thought about gravity being some invisible rope that pulls things together. Einstein's general relativity just threw that idea out the window. He said that big objects like planets and stars don't exert a force. What they do is they literally bend and warp the fabric of reality around them, this four-dimensional fabric he called space-time. So planets orbit the sun not because they're being pulled, but because they're just following the straightest possible path through that curved space. So the first huge consequence of this theory is that space isn't some static, empty background. It's a dynamic, flexible thing. And when you put mass into it, that fabric gets curved. But believe it or not, that's only half the story. Because space and time are actually woven together into space-time. So what happens to one affects the other. In a really strong gravitational field, it's not just space that's getting all bent out of shape. Time itself actually slows down. The stronger the gravity, the slower time ticks for you, compared to someone far away. It's truly mind-bending. This theory was just so profound, so elegant in the way it described the universe, that the physicists Lev Landau and Yevgeny Lifshitz called it the most beautiful of all existing physical theories. I mean, that says it all right there. It's like a masterpiece of art that also happens to perfectly describe reality. Okay, so now that we're armed with this new way of thinking about gravity, we can finally understand how these cosmic monsters are actually born, and it all starts with the spectacular death of a truly massive star. The whole process is incredibly violent, but pretty straightforward. See, for its entire life, a giant star is fighting a war with itself. You've got the outward push from nuclear fusion in its core, balanced by the inward crush of its own gravity. But eventually, the fuel runs out, fusion stops, and gravity wins. The core collapses in on itself catastrophically. The outer layers get blasted away in a supernova, and what's left behind is a remnant so unbelievably dense that nothing can stop its final collapse. And this visual really just shows that lifelong battle perfectly. For millions and millions of years, that stellar furnace is pushing out, creating all the energy and light we see. But the whole time, gravity is just relentlessly pulling in. And for the biggest stars, when that furnace finally goes cold, the collapse is just inevitable. So this is where Einstein's delightful weirdness comes back into the picture. As that stellar core collapses, the gravity on its surface becomes so intense that time slows down to a crawl for anyone watching from a distance. We would never actually see the star disappear. Instead, we'd see its final moment frozen in time, its light getting redder and dimmer, literally stretched out over an eternity until it just fades to nothing. Okay, so theory tells us these things should be out there, but if they're really, truly black and completely invisible, how on earth do you find one? Well, this is where astronomy turns into a cosmic detective story. I mean, this is the fundamental challenge for astronomers, right? You can't just point a telescope and snap a picture of something that gives off no light. So instead, you have to look for the clues it leaves behind, the fingerprints it leaves on the universe around it. And astronomers have gotten really good at spotting these clues. For instance, sometimes they'll see a normal star and it looks like it's orbiting nothing, but they can measure its orbit and figure out the mass of its invisible dance partner. If that mass is huge and crammed into a tiny space, well, you've got a suspect. An even better clue is when a black hole is actively feeding. Material gets torn from a nearby star and forms this superheated accretion disk, which glows like crazy in X-rays as it spirals in. And if those X-rays flicker chaotically in just milliseconds, it tells you the source has to be incredibly small. So, with all these powerful telescopes we have, both on the ground and up in space, astronomers are constantly scanning the skies, looking for these telltale signs, the wobble of a star, or the fierce glow of that accretion disk. They aren't seeing the black hole itself, they're seeing the shadow it casts on the cosmos. And here we have it, the case file for the very first major breakthrough, a system called Cygnus X1. Astronomers saw this massive supergiant star orbiting an invisible companion that was about 10 times the mass of our sun. And crucially, it was also one of the brightest X-ray sources in the sky, and those X-rays were flickering like mad. Every single clue pointed in one direction. Cygnus X1 became the very first, widely accepted black hole candidate. Case closed. You know, finding objects as powerful as black holes really changed how we see the cosmos. It made us realize that gravity could be the ultimate decider, not just for stars, but for the fate of the entire universe. So, how does this story end? The fate of everything really hangs in the balance of this cosmic tug-of-war. You've got the momentum from the Big Bang pushing everything apart, and on the other side, you have the collective gravity of all the stuff in the universe, including countless black holes, pulling it all back together. If expansion wins, the universe just gets colder and darker forever. If gravity wins, everything could eventually collapse back in on itself in a big crunch. And this brings us to one last really deep idea. Because the universe had a beginning, about 13.8 billion years ago, there's a limit to how far we can actually see. We can only see the light that's had enough time to travel to us since the Big Bang. This creates what's called a horizon of visibility. It's not a wall out there in space, it's a boundary in time. This cosmic lighthouse idea is a perfect analogy. We're looking at the past, and there's a point beyond which the light just hasn't gotten to us yet. So, we end right back where we started, with questions that just push the absolute limits of what we can understand. From those invisible stars imagined centuries ago, to the warping of space-time itself, to the ultimate fate of reality. Black holes aren't just objects, they're like cosmic laboratories for the extreme, forcing us to ask the biggest questions of all. What came before the beginning, and what is really waiting for us at the very end?